Perfect. Okay, I think we can start.
Yes.
Okay, Ivan. Okay.
Okay.
So, hello everyone. Good afternoon in Europe, and I think good afternoon in the rest of the world in Asia. So, welcome to the iteration of the European Non-Associative Algebra Seminar. We are here again every Monday, and it is my pleasure to introduce our speaker for today. He is in a PhD student about to graduate from Universidad de Málaga in Spain, and he's gonna talk about the affine group scheme of the automorphisms of evolution algebras of dimension 2. Help me welcome our speaker, Iván Ruiz Campos.
Thank you, Alfie. Thank you, the organizer. Thank you, Ivan. And thank you, all the participants, for being here and hearing this talk. I hope it's going to be as fun as I can make it. So I'm going to be talking about, I think, the affine group scheme of the automorphisms of evolution algebras of dimension 2. But this will be just a tool to study representations of the evolution algebra of dimension 2. This is a joint work with Yolanda Cabrera, Daniel González, Marines González, Dolores Martín, and Cándido Martín. Some of you, if I'm not wrong, might know them. They're some of my colleagues. Okay, so now. So this is what we're going to talk today. And first of all, what we're going to see is a little bit of preliminaries. Maybe some of you might know what evolution algebras are, but I don't think most of you know. So I'm just going to do a brief introduction and also do a motivation for what is this talk about. Then we'll see the affine group scheme and its relation with the Hopf algebras. Very easy. We will be using a Waterhouse book, so we'll make it as easy as we can. And then we will focus on the affine group scheme of automorphisms of an evolution algebra. Why? Because through that, we'll see a connection with the associative representation of evolution algebras. And finally, we will connect all of this together. Okay, so let's start. So as a motivation, let's consider this associative unital algebra as a quotient of the two-variable polynomial set with this ideal here. And in this algebra, we can consider an involution induced by this mapping. Just basically, we send the x to y squared and y to x squared. And under these settings, we can consider a product, a twist of the product using the involution that we have. And also we can consider a vector space A generated by x and y. Okay, so in this new product, in this set, we have that x times x equals y, y times y equals x. And if we multiply x times y, we obtain 0. And basically, this is just an evolution algebra. AP is an algebra with this property of orthogonality. It's an evolution algebra. So it's an evolution algebra contained in U. So something similar, as you might know, happen in Lie algebras. As you already, I think most of you will find very easy that if we have a Lie algebra, then G is a subalgebra of this Q-symmetric subalgebra algebra of its universal associative envelope. Okay. So we gain an associative algebra that we can contain the Lie algebra in, but we have to twist the product, in this case, making it Q-symmetric. So we obtain something that we can call like a representation of the Lie algebra, in this case, which is faithful. We also gain some new properties, or at least this algebra, this universal associative envelope has some good properties, which are that they also are a Hopf algebra relative to these coalgebra operations with this co-multiplication, co-inverse, and augmentation given here. So as we see, we have representations, we have a twist in the algebra, in the product of the algebra, and also obtain Hopf algebras. So we're going to try to relate all of this, but in the context of evolution algebra, in a similar way that happened before. So our work is a continuation of this paper by Marines Gonzalez, but my colleagues before, and also Mercedes Siles, where they studied automorphisms and representations of evolution algebras of dimension 2. And they saw that there might be a correlation. And this correlation is what we studied and finally confirmed the conjecture using Hopf algebras. You can find it in this paper over here. And basically, this talk is going to be about this paper. So if you want to do something else, you can skip it and just go and read the paper. Okay? For the ones who remain here, let's see what evolution algebra is. So they were introduced by Tian and Buchetowski in this paper here. And basically, it's an algebra with an orthogonal basis in the product setting. I mean, we say that a k-algebra is an evolution algebra if there exists a basis for which the product is 0 for different elements, and we say that this basis is natural. This algebra is non-associative. We have a very easy example of an evolution algebra that it's not associative, most of them. Basically, if you consider an algebra with the square of an element being different than it and the square of other element being different from 0, if we multiply, we obtain two different elements. It's not an associative, but it's commutative, which is, for me at least, quite interesting that we have we don't have associativity, but we have commutativity. And once you know the basis, you can compute all the products just by knowing the square of each of them, being the gamma, ak, the finite numbers, and being the structure matrix constants. If we have an evolution algebra with a natural basis, then as I mentioned before, with the structure matrix, we can put it all together and build this matrix over here that gives us some information. Well, it gives us all the information because it's encoded here. For example, one other thing that tells us if the algebra is perfect, at least in the finite case, an evolution algebra is perfect basically if the square of the algebra equals the algebra. And in the finite setting, in the finite dimensional case, this is equivalent to the determinant of the matrix being different from 0. Okay. Once we have an evolution algebra, we can consider the graph associated to this algebra. This was an idea by Alberto El Duque and Alicia Labra in this paper here. And basically, if we have an evolution algebra with a natural basis V, we can just construct this graph given by, we have one vertex for each element in the basis, and we have one arrow for each structure constant that is different from 0. And we have that the arrow goes from the vertex Vi to the vertex Vj if this structure constant is different from 0. Let's see an example that I think will make things easier. So we have an evolution algebra with dimension 2. In this case, the base field is R, given by this multiplication here. Then the directed graph associated is the following one. So you can see, for example, this structure constant here is different from 0, which means that the vertex V1 corresponding to the element E1 has a loop here, okay? But usually we don't use this notation. We prefer to use the label graph, which is basically just changing the name to, instead of V, using the elements in the basis, and instead of this general name, using the labels of the structure constant. So we would have something like this, okay? And this encode all the information in the graph, in the evolution algebra. It tells you how you multiply the elements, etc., etc. I would like to highlight, in the case of directed graphs for evolution algebras, that the associated graph depends on the chosen basis, and there are properties that cannot be deduced from the graph, at least not from the directed graph. From the labeled graph, you can obtain many information. For example, something that you cannot obtain is if they are perfect or not perfect. And also, different evolution algebras can have the same graph. For example, the evolution algebra with a structure matrix here has exactly the same directed graph as we had before. In the previous case, we have a perfect evolution algebra, and in this case, it is not perfect because the determinant is 0. Okay. So since we're going to focus on evolution algebra of dimension 2, it would be interesting if we had all of the possible evolution algebras of dimension 2. This is something that, once again, in this paper that I mentioned before, my colleagues studied, and they found all the families of evolution algebras on dimensions 2, which are 10 families. Some of them depending on some parameters, like this one over here. And I'm going to go through them very quickly just to show them, at least so you can have it in the recording and in the slides in case someone wants to keep the slides for them. Okay, so the first one is the easier one. It's the trivial algebra that you have. You have dimension 2 and the product is 0 for everything. Then we have the perfect evolutional cases. We have A1, which has this representation in the graph, A2 alpha, which is different for every alpha, different from 0, A3 alpha, A4 alpha, which is something like that. Again, depending on a parameter alpha. And for A5 alpha beta, we have that A alpha times beta has to be different from 0 and different from 1. Then we have the non-perfect ones. We have here, determinant equals to 0. Again, determinant equal to 0. You can see that because you have a sink and a source. Same happens here. Same happens here. This one and this one also are associative, which is important to mention. We will see that later. So, okay, we have evolution algebras of dimension 2, but what are we going to do? At least what I'm going to do in this talk. So we want to check if there is a connection between the automorphisms of an evolution algebra of dimension 2 and its faithful associative unital representation. So this will be the process. We will compute the automorphisms of all the families of evolution algebras of dimension 2. This is going to be by brute force because the second part will be study the corresponding affine group scheme, again, brute force by hand, and check if they have a faithful associative representation and compare each of them and see what are the relations. Good. So before doing that, before knowing at least what a representation in this case is, let's wait for the future. Let's see what an affine group scheme is. At least the easy way, I'm not going to talk about group schemes in general. We'll just follow the functorial way, following this book over here from Waterhouse, Introduction to Affine Group Schemes. And basically, an affine group scheme is a functor from the category of commutative associative unital algebras to groups, in such a way that if we compute this functor with the forget functor, going from out k to sets, this functor is representable, which means that there is an algebra such that for every k algebra R, there is a bijection from the group, in this case, to the homomorphisms from A to R, okay? And this algebra is the algebra that represents the functor, the affine group scheme, okay? There are some cases in which the affine group scheme also you can represent every element of it as a collection of tuples that satisfy certain equations, for example, Lie groups. So in this condition, under these conditions, the algebra that represents the functor f is basically the quotient of the polynomial ring with as many variables as elements in the tuple, quotient with a DL generated by all of the polynomials that have to satisfy these elements. Okay? As an example, for example, we can consider the affine group scheme mu n, which gives you the nth roots of 1. And in this setting, the algebra that represents this affine group scheme equals to the group algebra of the cyclic group. You can have the general linear group again, which are all the matrices of dimension n that has determinant which is a unit. And in this case, we have this as the algebra that represents the affine group scheme. And also mention another example, the multiplicative group, which is just the units in the K algebra, and the algebra that represents this functor is just the Taylor polynomials. Okay, good. So if we recap, we have an affine group scheme, and it can be represented using an algebra. This algebra has some properties, and this is because, as I mentioned before, the affine group scheme, the functor of a ring, well, not a ring, of an algebra, is a group. Since it's a group, we have a product, we have an inverse, and we have an unit. And they behave very well. We have the product, the inverse. And the unit, we can see it as an injection of the trivial group in the group. And in this case, you can prove that for an affine group scheme, all of these morphisms are in particular natural maps. So we can make use of Yoneda's lemma, which says that if we have two representable functors and a bijection between the set of natural, there is a bijection, between the set of natural maps, all the natural maps between the two of them, and the homomorphisms between the algebras that represent the affine group scheme. So if we translate these natural maps into morphisms from the algebras that represent each functor, we have the following morphisms. We have the commultiplication, we have the coinverse, and we have the augmentation. And since the product, inverse, and unit have different properties about commutativity, and also about associativity, etc., 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 we can then induce these properties for delta S and epsilon. And basically, this means that the algebra that represents the functor is a Hopf algebra. Okay, so we know what an affine group scheme is. We already know what an evolution algebra is. Let's study a way of building an affine group scheme from an evolution algebra. And basically, what we build is the affine group scheme of automorphisms of the evolution algebra. So if we have an associative unital K algebra and A an evolution algebra, we can consider its scalar extension by using the tensor product, which is basically isomorphic to just considering the R module of R span, of the basis. Okay, so once we have that, basically the affine group scheme works in the objects as you have an algebra, and then you just consider the set of all automorphisms from the scalar extension with this same algebra. In the case of the morphisms, it's a little bit trickier. Don't get lost. This is just because I wanted to get into the definition, but we will not focus on that. This is well defined, and it's a very well-known function. Okay, so one way of building all these affine group schemes is using, at least for the perfect finite dimensional evolution algebras, using this paper by Alberto Duque again and Alicia Labra, in which we have that this sequence here with the diagonal of the graph of the evolution algebra and the automorphisms of the graph of the evolution algebra, it's exact. So if we know this and we know this, it is possible to compute this affine group scheme. We will make use of this result and some other properties related for A1, A3 alpha, A4 alpha, and A5 alpha beta. But for the non-perfect case, and for another ones, we will appeal to just the classical computation by basically brute force. Okay. So how do we do this? How do we compute all the automorphisms, and also how do we build the Hopf algebra? So if we have an algebra of dimension 2, and we consider an automorphism in the extension of the evolution algebra, knowing the base, we can consider that the image of E1 is this combination, the image of another element of the basis is this combination here, being A, B, C, and D elements in the algebra. And in order to have a morphism, it needs to verify these three equations here, And also to be invertible, the scalars needs to verify this here. Let's see an example. So if we consider the algebra A6, which is basically given by this multiplication table, then an automorphism here verifies all of these equations, okay? V squared equals to 0, B times D equals to 0, A equals to D squared, B equals to 0, and D to the power of 3, it's a unit, okay? So if we resolve this system, what we get is that the automorphisms is equivalent, it's isomorphic to this set here, okay? With the group operation given by just the product and the inverse by the matrix inverses. So we can see the elements here as tuples of the form X, Y, and Z. Why? Because we have basically, this is the square of this element. So we have all the information encoded in C and D, but also we have that D is a unit. So we need to add extra information that tell us that this element has an inverse. So that's why we can see automorphisms of tuples of 3 elements with Y times Z equals to 1, and with the product given here with it. Following the Waterhouse book and some properties of the Hopf algebra and the affine group scheme, and Joneda's lemma in particular, we can prove that the Hopf algebra, the algebra that represents this affine group scheme, basically is given by this co-multiplication, this co-inverse, and this augmentation, okay? Good. In some cases, the characteristic of the field plays a key role. So as an example, let's consider A5. And we have that after some computations, this is the set of automorphisms. Make sure, look that we have a 2 here, so we have to be careful with the characteristic. So if the characteristic is different from 0, then the affine group scheme is isomorphic to the multiplicative group, okay? Which is represented by this Hopf algebra with this coproduct, co-inverse, and augmentation. However, if we consider characteristic 2, then things change, and we obtain that the affine group scheme of automorphisms is actually the additive group, and we have a different co-multiplication, a different co-inverse, and a different augmentation. So here, after lots of computations that you can even check in the paper, these are at least the perfect evolution cases where we have the algebra, its corresponding affine group scheme, and the Hopf algebra that represent the automorphisms of the algebra. See that in some cases we have that the automorphisms are trivial, just the identity. In this case, the Hopf algebra is the ground field. And for the non-perfect case, we have to be careful with the characteristic being 2 or different from 2. And again, we have different combinations of the multiplicative and the additive affine group scheme. Okay, good. So once again, trying not to get lost, let's recap. We have evolution algebras of dimension 2. We have the corresponding affine group schemes. Okay, we already know that. Let's see, let's study their universal associative unital representations. And in particular, we will see the faithful universal associative unital associative representation and what they are. Okay, so they were introduced in a general non-associative context by Alexander Kornev and Ivan Shestakov. And basically, the idea is the following. So for a 2-dimensional case, which is the one that we have, we consider the polynomial algebra with these 4 variables and an involution given by x goes to x star and y goes to y star. If we consider 4 scalars here, we can make a twist in the product here by this combination here. And what we want with this twist is building a quotient that allow us to inject our algebra. The algebra that we want to embed is a two-dimensional evolution algebra in general with natural basis E1 and E2, and the product being general with the structure constants. So what we'll do is we build a star ideal I, such as there is an homomorphism of evolution algebras. And this homomorphism of evolution algebras behave well with the twisted product. Okay, so we can embed the algebra in an associative algebra because, as we know, this is associative, and when we have a quotient, it remains associative. Okay, good. Any questions so far? Because maybe I'm going too fast or something. You can interrupt me if there's any moment that you feel that you get quite lost or something like that. Okay? If not, I shall continue. Good. Okay. So we want to build an star ideal in order to embed the evolution algebra. And the ideal is basically generated by the star ideal generated by these elements here. We want that the twisted product equals to the product of the algebra for these two elements. And also we want that the product of two different elements equals to 0. So the representation that we have is just given by the image of E1 going to the equivalence classes of X and the image of E2 going to the equivalence classes of Y. And this is called the associative unital representation of A. And the algebra EUP is the universal unital p-algebra. When the representation is faithful, we say that it is the full universal unital p-algebra. And it is universal in the sense that we all hope that if there is another associative unital representation with an involution, then there is a morphism of unital algebras with involution, such as you can decompose it using the universal associative representation and the morphism that we have. If instead of using the whole algebra, we keep aside the units and we just focus on the ideal, on the vector space generated by these elements, that is the free associative commutative algebra without units, and we repeat again the same construction. Instead of rho, we have a homomorphism R being type P, this quotient here, and this is what we talk about, the tied universal associative representation of A. Once again, if the representation is faithful, we say that the type P is the faithful tied universal p-algebra. Let's see an example. Very, very easy one. You will see that. We will see why later. So if we consider A1, an evolution algebra of dimension 2, that has E1 squared goes to E1, E2 squared equals to E2, then as a representation of it, we can just consider the polynomial ring with two variables and the involution given by the identity. The product, or the twisted product that we can consider, is just the same product since, well, the involution is the identity. So once again, we consider the ideal generated by these elements here, as we wanted before. And the universal p-algebra is just this quotient. And the representation given is faithful. It is faithful because X and Y under this condition, or at least in this quotient here, is a linearly independent set. This is not a, well, this is maybe the best representation that we can give, which is quite easy that we can give this associative representation, because basically, well, first of all, I said that in this case, yes, I mentioned that before. Basically, this is the best representation because the algebra, it's already associative. There's nothing new. So under this construction, we obtain the best representation that we can have, which is itself. It is also isomorphic to the tied type P algebra and also to the Hopf algebra, as I mentioned before, because A1 is associative. So nothing new, just small example, so we can check that at least for the easy cases, everything works. So again, recap: we know evolution algebras, we know the affine group scheme, we now know what a universal associative representation is. So let's study all the universal associative representations of at least trying to find the faithful ones. So the strategy to find the faithful ones is the one. We consider an evolution algebra with one of the known families. And then we take the polynomial PAV given here, that is our twisted product. That's what we'll twist, so we will obtain the representation. And we have two possible ways. The first one is we find the scalars that makes the twisted, the associative representation faithful, basically, that makes x and y linearly independent in the algebra, or the other possibility that we have is explore all the possible values of lambda I and see that x and y are not linearly independent. That is, they are linearly dependent, so there are no faithful associative representation. This is very tricky. This is pages after pages of computation. At least, I don't know if it's more boring reading them or just doing them. Up to you to choose that, to see if they are not. So apart from doing brute force and doing all the computations by hand, very tricky again, we use some results, thank God. And one of them says that if we have a perfect evolution algebra and we have a faithful representation, such as this element and this element belong to the ideal, then the only possibility that we have is that A is isomorphic to A1, A6, or A7. Basically, that the algebra is associative. And in a very similar way, there is also this lemma that if we have, again, a faithful representation in which x minus x star and y minus y star belong to the ideal, then again, the algebra is isomorphic to one of these three, which means that the algebra is associative. So using these results, using brute force, what we obtain is this family here, well, not this table here that condenses all the information. We have for A1, A2 alpha, and F5 alpha alpha, we have faithful representations with this twisted product. And for these three, we don't have faithful representation. Again, this doesn't mean that we don't have a universal representation. It means that there are not any faithful ones, okay? This is for the perfect case. And for the non-perfect case, again, the characteristic of the field plays a key role. We have more faithful for the non-perfect case, faithful representation, but we don't have faithful for the A8 alpha with characteristic 2. So we have all the representations. Well, we have the representation if they are faithful or not. We have the evolution algebras. We have the Hopf algebra associated to the algebra, the affine group schemes. Let's put it all together, compare, and see what we can see. Hopefully, maybe you already know what we have. So we can summarize all of this in the following theorem that says that for a two-dimensional evolution algebra A over a field K, the set of automorphisms is trivial if and only if there are no faithful p-algebras for A, faithful representation p-algebras. And if the Hopf algebra that represent the affine group scheme, there is an associative representation. Well, sorry, there is a faithful associative representation for A if and only if one of the following holds. which basically, if the characteristic is different from 0, then the Hopf algebra, it has to be different from K. If it is equal to K, then there is not a faithful associative representation. And in the case of characteristic 2, the Hopf algebra of the affine group scheme has to be different from, again, K, or different from this quotient here. Furthermore, if the algebra is perfect and has a faithful tight p-algebra, then this tight p-algebra is isomorphic to the Hopf algebra. So we can obtain representations by computing the Hopf algebra. We can see here, at least for the non-perfect case, that for the faithful case, we have that the Hopf algebra is different from K. For the not faithful case, we have that the Hopf algebra is equal to K, again here, and the tie representation is isomorphic to the Hopf algebra. Here doesn't appear because it doesn't make, at least we haven't computed it, okay? At least not because we don't have a one canonical faithful representation, okay? And for the non-perfect case, we have all of this. We have lots of faithful representations, again, because the Hopf algebras are different from K, but in characteristic 2, in this case, automorphisms equal to 1, we don't have a faithful representation, and the Hopf algebra is different from, again, when in this case is equal to this one, which is different from K, but it remains not true. So I think I went very quickly, I have to say. Well, you can find all of this information in, as I mentioned before, in this paper right here, which is the one that condensed all of it as a first part. You can also check this paper here. And basically, that was all. Thank you so much. So sorry, I went very fast, I have to say. I thought that it was going to be interactive more, and I thought that it was going to be maybe get some more minutes, but yeah, that's pretty much all. Thank you so much.
All right, thank you so much, Ivan, for that very informative and not so fast. It was very good pacing, don't worry. For that wonderful talk, thank you. If there are questions from the audience for Ivan, I think, okay, one raises hand, Paulo Saraco.
Yes, hi, thank you very much. Thanks, Ivan, for the presentation. Sorry, I just have a curiosity. Do you mind to go back to where you constructed a affine group scheme associated with an evolution algebra?
Mm-hmm. Let me check. Here?
Okay, wonderful. So, your evolution algebra, you said that in general is non-associative. So this means that also when you extend the scalars, what you get is non-associative in general,
Yeah,
isn't
it
it?
remains not being associative.
Okay, nevertheless, here when you're considering the automorphism group as non-associative algebras.
Mm-hmm.
Is it correct? Okay. And how hard is it to see that this is representable by something associative?
Could you repeat? I don't really understand what you mean. Sorry.
Well, okay.
Like, I mean, you can study automorphisms of an evolution algebra, and also you can study for the scalar extensions. And basically, the automorphisms form a group. So you have a functor that goes from K algebras to groups, and in this case, it is representable in general. Well, maybe not in general, but at least for the finite case. Well, first, this paper here that I think I haven't read it completely, I have to say, but I think they make use of it. And in the finite case, basically because we give the representation of, we give the algebra that represents the automorphism setting. And also because one way of seeing affine group schemes, at least the very trivial one, is like basically if you have a family of equations that are the ones that define the group, then this is an affine group scheme. There is a correlation between them. In the first chapter of the Waterhouse book, they prove that, they make use of it, and this is what I have followed. I don't know if there's something more general that I'm not considering, or maybe because if maybe you're thinking about schemes in general. I have no idea. I just know this setting.
No, okay. I was just curious because when I learned them, I thought you were needing commutative algebras, commutative associative algebras, but okay.
Okay.
Okay, thanks. Sorry.
You're welcome.
Thank you, Paulo. There's also a question in the chat. If you can read, Ivan, I can read for you.
Chat, let me check. I see. Thank you for your talk. Please comment on the connection between evolution algebra and your. Oh, I have to say, I'm not. Even though I know many people that is familiar with Jordan algebras. I just know the very basics of Jordan algebras, and I don't really know the connection of evolution algebras, because actually this is not the issue of my dissertation, of my thesis dissertation. This is just something extra that we did. And since what I work is in associative algebras, so this is the only non-associative paper or something like that I had. That is why I decided to make use of to talk about it. But I don't really know much about Jordan algebra. It's very naive. I'm very naive for that. So I don't know if maybe you know something that you would like to tell us, but I don't know. I don't really know. I just know that it's that it's non-associative and also it's commutative. So no, that's very much. I don't know.
Okay. Are there other questions for Ivan? If none, I think we have plenty of time for questions. Can I ask a question? So I have two questions, and please forgive me if my question does not make sense. So did I understand correctly that the graph not necessarily view your evolution algebra, but in the case of dimension 2, it does, because you're able to classify them? Well, is that correct? You mentioned there are multiple evolution algebras not having the same graphical representation. And for dimension 2, you had this.
We have no, but we have. How do I explain this? Okay, so in dimension 2, you have that if you have an evolution algebra, then it is isomorphic to one of these families, and then you represent each family with this graph. Okay, but in general, you can have an evolution algebra, and if you have two different natural bases, the algebra remains the same, but the bases are different, and both of them are natural. It can be possible that you have two different graphs for the same algebra. This is something that doesn't happen for perfect evolution algebra, because for perfect evolution algebras, all of the bases are just reordination of them and scalar multiplications of them. So the graphs remain the same or isomorphic. But in general, in dimension 2, I don't know if you can have right now, because I'm not really. I don't know if there is a representation, if there is an evolution algebra with representation of two graphs. I think you can have it, But even though you have two different graph representations, it remains isomorphic to one of them and to one of the families. And those families, with the setting that we gave, the representation is that one because we chose the natural basis. But once you change the natural basis, everything can change. Unless for the perfect case. Except for the perfect case.
I see. Is this also telling us that it...
Oh. I couldn't hear you. I think the connection got lost for a moment. Can you repeat?
Okay, no worries. Yeah, no problem. Is it also telling case, not dimension 2?
Again, something, I don't know what happened. It was just me or the rest happened the same?
I think it's my internet. I'm so sorry.
No, it's not your fault. You don't have to be sorry. You can maybe write it down if you want.
Hello.
Hello, Wolfie.
I am back. Sorry, I just changed my internet. It was me. So sorry, Ivan. So again, my question is it then telling us that it's perhaps harder to extend your work on higher dimensional case? Especially you've mentioned earlier that there was a lot of cumbersome calculations that you have done.
Yeah. The thing with evolution algebras is that many weird things happens there. Since the being non-associative and being commutative, and also being an algebra that it's not a variety, which is something that doesn't happen to Lie algebras and Jordan algebras. For example, if you have a Lie algebra and you have a subalgebra in it, you still have a Lie algebra. Your algebra remains being a Lie algebra, and that's something that doesn't happen for evolution algebras. If you have an evolution algebra, you can have a subalgebra of it, and that algebra not being an evolution algebra. Okay, so very, very weird things happen, and in those settings we really rely on computations, and just for dimension 2, computations got very, very tricky, very hard. Like at first the paper was like 40 pages of just computations, and we made things we try to shorten things up. So if we want to make it to a higher dimensional level, at least for the non-perfect case, things are very hard, very tricky. But for the perfect case, there is a paper that recently where they proved that for the perfect evolution algebras, a subalgebra of a perfect evolution algebra is an evolution algebra. So maybe for the perfect case, things got easier. Maybe things go smoothly. Maybe we can obtain more results that allow us to compute, to not make use of the brute force, as in Lie algebras and algebras. But at least for now, in the more general setting, at least I don't know if there is an easier way. I think not for now.
Okay. Good question to ask for future research. Final question from me. So you, if I understood correctly, you were constructing in two different directions, but meeting in the same point where you started through the evolution algebra and compared these two research, these directions. One on the direction by the affine group scheme with Hopf algebras, and one in the universal representation area. And you mentioned that it was a very cumbersome process to solve all of these things, but which area would you say was way easier or harder comparing them, just to see perhaps a good easier direction to do
okay that? So it was way easier just to compute the affine group scheme. Very, very easy, at least for dimension 2. The equations that you have to solve were not very tricky at all. We can also make use of the result of Alberto El Duque and Alicia Labra of using the exact sequence. The hardest part was definitely trying to find a faithful universal representation of the Hopf algebra, of the evolution algebra. Many cases were known for the faithful one, but proving that there is no faithful representation was the trickier one, because we have to be working step by step, little by little, by making certain considerations, like, okay, we have this ideal. Let's try to prove that X and Y belong to the ideal under different conditions in the scalars, in the lambda 0, lambda 1. So first, we did things like, okay, if lambda 0 equals to 0, then we make this. If this, so it was very, very long. And in the end, we used some of like mathematical things like that, but just to make sure that we did all correctly. Like we did all by hand. We didn't just trust Mathematica, because maybe we could have used Grebner basis and things like that, but it wasn't that easy. But yeah, definitely affine group is computing the automorphisms were very easy. Also because this is something that at least they did before in the paper, at least for some of the examples in the first paper that I mentioned.
Okay, perfect. Good to know. Okay, there is a comment in the chat. Some of the evolution algebras in today's talk are also Jordan algebras. It remains a research problem. Thank you again. From the same person, Gloria Nichita. All right, are there further questions for Ivan? Yes, please.
Yeah, sorry. I managed more or less to focus what was bothering me before. Okay, if your algebra in the definition of an affine group scheme, so the algebra R is non-commutative.
No. In the algebra R is associative, commutative, and unital. The one that is not is the evolution algebra.
Okay.
But the extension, it is with the ring, the R, it has to be, because we define, or at least we work with affine group schemes of commutative associative functors that go from the category of associative, commutative, unitar algebras to groups.
Okay. So your small alg K is commutative associative algebras.
Exactly. Yeah.
Okay. Thank you very much.
Now I see why you were not. Okay. Thank you.
Okay, so there's also a comment, a reference coming from Ivan. Okay, are there other questions? And this is also being shown in the... Oh, no, I thought it was being shown, sorry. Any question for Ivan? Okay, I think there are no questions anymore. Let's thank our speaker for today for giving us his time, his precious time, as someone who's about to defend soon. I'm a very busy guy. Thank you, Ivan, for giving us this talk. We really appreciate it. And thank you to all of our attendees. And thank you for the organizers. I think it's about time to say goodbye. Correct, Javier?